Okay, folks, I want to address a question that I don't think I clarified very well in class tonight. The book uses the phrase find the general solution to an ODE, and I would prefer to keep using the phrase find a general solution. I don't think we're talking about anything differently, but I just want to stress that given two different fundamental sets, we might express a general solution differently. So they won't look the same, even though they will both be describing the same span of solutions. So let me show you what I mean by that. Given this ODE right here, one solution to it is the sine of x, and a second solution is the cosine of x. So these two may or may not form a fundamental set. Let's find out. So we look at the Wronskian of y1 and y2, and we find that that is the sine x, and then its derivative is the cosine of x, and then for the second solution we list it as cosine of x, and its derivative is minus the sine of x. And if we take the determinant of this, this is kind of fun, we get minus sine squared x minus cosine squared x, which just for the heck of it we could say is minus sine squared x plus cosine squared x, which is minus 1, which is certainly not 0. So that says that these two functions are linearly independent. And since they're linearly independent, and there are two of them, and we started with a second order linear ODE, we know that a general solution, so I would still use the phrase a general solution is y equals c1 sine of x plus c2 cosine of x. So there's a general solution to this ODE. The reason why I like to use the word a general solution as opposed to the general solution is because these two functions also form a fundamental set, and so a general solution to this ODE. If I pick the function the sine of x plus 1 and y2 is equal to the cosine of x plus 1, well, let's first confirm that they're solutions. Well, let's see here. If I take the derivative of y prime, I get the cosine of x plus 1, and if I take the second derivative, I would get minus the sine of x plus 1. So it seems clear to me that y1, I should write that as a double prime instead of a 2. That looks like we're thinking that's a squared. Y1 double prime plus y1 prime is, well, minus the sine of x plus 1 plus the sine of x plus 1 equals 0. So that is indeed a solution. And likewise, if I took y2 double prime plus y2, I don't know why I put a prime on this first one, folks. That should not have a prime on it. Well, that would be equal to, let's see, derivative of cosine is minus cosine, so this would be, derivative of cosine is minus sine, derivative of minus sine is minus cosine, so it would be minus cosine x plus 1 plus cosine x plus 1. So this also, so notice that both of these are solutions to the original ODE, and we could quickly check that their Wronskian is not identically 0. So let's see here, we'd have the sine of x plus 1, so we get the cosine of x plus 1, and then we have, let's see, the cosine of x plus 1, and then minus the sine of x plus 1, and in fact, interesting, well, I don't know if it's that interesting, we get similar Wronskian plus negative cosine squared x plus 1, factoring out the negative, we get sine squared x plus 1 plus cosine squared x plus 1, and so we get minus 1 again for the Wronskian. I'm not sure, I'll have to think about whether or not two different fundamental sets always have the same Wronskian if they are solutions to the same ODE. Interesting question for you to think about. Will that always happen if both fundamental sets are solutions to the ODE? Anyway, so here again we would say that a general solution is y equals c1 sine of x plus 1 plus c2 cosine x plus 1. So here we have two different general solutions to the original ODE. So I do not think that, I don't think I want to use the phrase the general solution. I think I want to use the phrase a general solution. But it turns out that, there's no real difference between these two functions. I can, for any function I can create out of this one, I could create the same function out of this one. So we'll talk about that in the next example.